This is from one of the handouts about partial derivatives and tangent planes. So we are looking here at a function that is given by 55 minus 5x squared plus 3y squared plus 10x minus 12y. So one of the first things would be to find the partial derivatives. And looking here at the function, if you take the partial derivative with respect to x, you just treat y as a constant. So it would kind of be used as a number. So 55 is a number. If you take the derivative, it turns into 0. The derivative of minus 5x squared is minus 10x. Then we're going to have 3y squared. Y is a number, so that derivative would be 0. And the derivative of 10x would be plus 10. And similarly, minus 12y. Y is just a number, so that drops out when taking the derivative. So we have that the partial with respect to x is just minus 10x plus 10. Now if you take the derivative with respect to y, you do something similar, but now you hold all of the x's as a constant. So 55, the derivative is 0, minus 5x squared, the derivative is 0, and then we're going to get 6y and minus 12, and the rest drops out. Now we want to find the partial derivatives and evaluate them at the point 1, 2. So that will give us the slope in the direction of x and y at that point. So we can say f of xy at the point 1, 2 well, if x is 1, then we're going to get minus 10 plus 10 equals 0. So that tells you actually that the derivative in the x direction is 0, means that it really is kind of flattening out at that point. You can do something similar and figure out what f of y is at that point. So the derivative in the y direction is 6y minus 12. X is 1, but it doesn't show up in the formula, so we don't care about that. Y is 2, so we're going to get 12 minus 2, 12 minus 12, which is 0 again. That is going to greatly simplify our formula later on. So the tangent plane is kind of, locally, if you would zoom in on the function there on the graph, if you zoom in close enough, you take any object, if you look close enough on a little disk, it'll look like a small plane. So in order to find that tangent plane, we have the formula that takes the derivative in the x direction times x minus x0, derivative in the y direction times y minus y0. That's a typo. And plus the function at 1, 2. So what is the function, the original function at 1, 2? We would have that, we just plug it in everywhere. And so we're going to get 55 minus 5 times 1 squared, so that's just minus 5. Then plus 3 times 4 plus 10 minus 12 times 2, which is equal to 55 minus 5 plus 12 plus 10 minus 24, which is equal to, going to get 22 minus 24 minus 7, that's 48. And so that means then that the linear function is going to be the derivative in the x direction, which is 0, times x minus 1 plus 0 times y minus 2 plus 48, which in this case actually just reduces everything down to just 48. Normally you would not have zeros here as the coefficients for the x and the y terms, and you'd actually get something with multiples of x and multiples of y plus some number. So we usually have these tangent planes to help us compute numbers and values nearby. And so because the linear function is just a horizontal plane, it means that the linear approximation of a nearby point would end up still being equal to 48. So it is saying that not only is it 48 at 1, 2, but we would expect that at a very small area around it, it's also going to be 48 or a number very close to it.